Hello friends, welcome to Susan and John MathTube. Today we are with lesson 6, and in lesson 6 we'll be learning two very important theorems from vectors. And before we start, these video lessons are specially designed for the first year engineering students in TU affiliated colleges. And this is lesson 6 of that video series, and as always, how to use the video lessons effectively. You can read these things and put them into practice if you want to make the video lessons effective. So these theorems are from your past paper questions, and I saw these questions being repeated in a few of the question papers. And one warning: don't expect that these are sure questions. If you really want to score good marks after watching these videos, it will work out a lot of questions. Only with practice you can make math strong, especially when you go for an exam. And these videos will definitely give you a strong base and boost that you want before you start preparing. Okay, and I like this quote. So let's start. So before we start the theorem, I want you to understand two small things. One is magnitude and the other is direction. So a vector will be associated with two quantities. One is the magnitude and the other is direction. When you go for the physical meaning of vector, magnitude means the amount, the quantity involved in the vector. But in math, vectors are very easy to study because we learn vectors to be line segments with directions. So all we can measure here is the length. So mathematically, magnitude will be the length of the vector, but the physical meaning will be different. And the direction, of course, we put an arrowhead to represent that direction. Anyway, remember, every vector will be associated with the magnitude and direction. And the second one we need is the formula for A dot B. And I'm sure you know the formula for A dot B. And one more very important thing. If A is a vector function, I'm not talking about constant vectors, about vector function, and let's say the function is written in terms of t, then the modulus of A will be a scalar function. So this is very important. Anyway, I'll give you one example. So take a look at this. A is equal to ti plus t square plus 1 into j. Clearly it's a vector function in t. When you input t equal to 1, you'll get one value. When you input t equal to 2, you'll get another vector, etc., etc. And now take a look at the modulus. It's not a constant, but it is a function in t. So that is exactly what this note implies. If you have a vector function in t, then the modulus will be a scalar function. So A generates vectors and modulus of A generates scalars. And now one more very important thing. Suppose we have a scalar function and a vector function, then the formula for finding the derivative of this combination, you can note this formula. And one more. Now suppose you have two vector functions. Earlier it was scalar function and vector function, but now both are vector functions. And when both are vectors, only dot and cross makes sense. And this is the formula to differentiate dot product. We have a similar formula for cross product, but we don't need that formula for the proofs. So the first proof is condition for a vector function to possess constant magnitude. So I told you, whenever you have a vector, you associate the vector with two quantities, magnitude and direction. Now the question is, what might be the condition for a vector function to possess constant magnitude? So there it goes. The necessary and sufficient condition for a vector function A in variable t. You just saw an example of a vector function in variable t. To have constant magnitude is A dot dA by dt equal to 0. Now look at this, the word necessary and sufficient. That means it's biconditional. That is, if you have a vector function with constant magnitude, then you can write A dot dA by dt equal to 0. Now if someone tells you A dot dA by dt equal to 0, then this implies A is a vector function with constant magnitude. So I'll write that here. Okay, so you have the theorem, the statement of the theorem over here. So look at this. This is exactly what we are trying to prove. A has constant magnitude if and only if A dot dA by dt equal to 0. So remember, this necessary and sufficient is just the biconditional statement. That means if you know this, you can use this, and if you know this, you can use the first one. Okay, so I'll keep that part over here. So the statement of the theorem and what we are supposed to prove. So let's go for the necessary part. In the necessary part, what we do is we will assume the condition on the left and we will prove the condition on the right with the help of this. So assume that A has constant magnitude. Magnitude is denoted by the modulus symbol. So it's given that modulus of A is a constant, and if let's say 5 is a constant, so definitely 5 square will be a constant. 10 is a constant, so definitely 10 square will be a constant. So squaring, we get another constant and I give it a name k. Now I hope you remember the formula for A dot B. In the beginning of the video we saw the formula. That will be mod A mod B cos of the angle between A and B. So using that formula, we can see that A dot A will be mod A cos. Yeah, what's the angle between the vector A and the vector A? Yeah, 0 degree. And that gives us A dot A equal to mod A square. Or in other words, mod A square is nothing but A dot A. So now look at the left side of the screen. We got mod A square equal to k because of the given condition. But mod A square is A dot A. Now remember, A is not a constant vector. It is a vector function in the variable t. So let's differentiate on both sides with respect to t. And I hope you still remember the formula to differentiate dot product. So I'm going to apply the formula A dot dA by dt plus dA by dt dot A. And you know that A dot B and B dot A are the same, so we end up with 2 times A dot dA by dt equal to 0. Now if someone tells you A into B equal to 0, you will understand that either A will be 0 or B will be 0. Now look at this. We have A into B equal to 0. But 2 cannot be 0. So definitely A dot dA by dt will be equal to 0. Okay, so that's it. Take a look at what exactly we have to prove? We assumed this. Look, we assumed A has constant magnitude, and we proved the right side. Now for the sufficient part, what we do is we start from here. We trust the right side. That is, we trust A dot dA by dt equal to 0. Let's call it equation number 1. And I hope you remember A dot A is mod A cos 0. That means A dot A equal to mod A square. And that means mod A square is A dot A, of course. Now we start the proof from here. I'm going to differentiate both sides with respect to t, and as before I applied the formula on the left side. And now take a look at the right side. Do you remember the note which we observed in the beginning? If A is a vector function, then modulus of A will be a scalar function. So definitely mod A square is a scalar function. For example, if I have tan t the whole square, how do you differentiate tan t the whole square? This is a scalar function. It will be like something square. The derivative of x square is 2x. So it looks as if it's in the format of something square, and the derivative will be 2 tan t, and then the derivative of tan t, which is x square t. Suppose you want to differentiate sin t the whole square. The same story, something square. So 2 into sin t, and then the derivative of sin t, which is cos t. Now look at mod A the whole square. I told you this is a scalar function. So the derivative will be 2 into mod A, and then the derivative of mod A. Oh, but what is our assumption? Our assumption is A dot dA by dt equal to 0. Wow. So this side is going to disappear. This side is going to vanish. And that means now I'll write there is 2 mod A d by dt of mod A equal to 0. And I asked you a little bit earlier, what does it imply if someone tells you A into B equal to 0? Of course, it implies either A will be 0 or B will be equal to 0. So we have something like that over here. A into B into C is equal to 0. 2 cannot be 0. And modulus of A cannot be 0, because if modulus of A equal to 0, then A is a 0 vector. And A being a 0 vector, this theorem will be trivial. So the only possibility is the derivative of modulus of A must be equal to 0. This cannot be 0, this cannot be 0, so the derivative must be 0. Now you tell me whose derivative is always equal to 0? Yeah, that means modulus of A is a constant, because the derivative of a constant will be 0. Okay, that's exactly what we are trying to prove. We started from here, you can see that, assume that, and we ended up with A has constant magnitude. Okay, that's it. Now let's move ahead for the second proof. Okay, condition for a vector to possess constant direction. Of course, a vector is associated with two things, magnitude and direction. In the first theorem, we were talking about constant magnitude. So in this theorem, we will be talking about constant direction. And the statement also looks similar. The necessary and sufficient condition for a vector function A in variable t to have constant direction is, okay, in the last theorem it is A dot dA by dt equal to 0, and here it is A cross dA by dt equal to 0. So for constant direction, this is the condition, and for constant magnitude, the same thing but dot product. Okay, and it's a necessary and sufficient condition, so I'm going to write in the biconditional style. I don't like writing necessary and sufficient, so I'll make it if and only if condition. So A has constant direction if and only if A cross dA by dt equal to 0, and I'll keep it on the right side of the screen. So how do you start with the necessary part? Assume this and prove this side. And the sufficient part, assume this but prove this. Okay, but before we start, we must find A cross dA by dt. The proof is slightly different than the first one. So I hope you remember the formula for unit vector. And once more I'll remind you, if A is a vector function, then modulus of A is a scalar function. In the beginning of the video we saw this. And one more thing, unit vector will be a vector function. And I hope you still remember the definition of unit vector. Let's say this is a vector. You divide this into equal parts and draw a vector parallel to this but with one unit length, and that will be a unit vector. So remember, a vector and unit vector share the same direction. So what is common to a vector and a unit vector? The direction. Okay, so I'll just cross multiply. So every vector can be written in the form modulus of A into unit vector. Remember, A is a vector function, it's not a constant vector. Now let's differentiate. In the beginning of the video I gave you a formula how to differentiate scalar function in T and vector function in T being a product. So the rule goes first function derivative of the second plus derivative of the first. Okay, so I'll repeat, I'm trying to find this quantity A cross dA by dt. So now what I do is I'll take cross product on both sides. I know the value of dA by dt, so I'm going to take cross product on both sides. Now let's distribute this, and I hope you still remember the first step of the proof. Vector is modulus of A into A cap. Okay, so we are almost near the value of A cross dA by dt. Okay, now one important thing. Suppose we have something like 7A cross 3B. What you do is you write this as 7 times 3, that will be 21A cross B. Now suppose you have something like T into A cross sin T into B. You can apply the same logic or the analogous logic, that will be T into sin T and then A cross B. Okay, now look at this. I told you A is a vector function, so the modulus will be a scalar function, something like T and sin T. And again we have the modulus, which is a scalar function, and the derivative of the modulus. Of course that will be a scalar function, it's not going to be a vector function. So I wanted to take a very good look at the second example, Ta cross sin T into B. We have two scalar functions, so I kept the scalar function as the product, then I took the cross product. So I'm going to apply the same thing. So mod A into mod A, that gives me mod A square and the remaining part. And here the scalar functions are modulus of A and the derivative of modulus and the remaining part. And A cross A is 0, so this part will disappear. Okay, so we found the value of A cross dA by dt. I'll do one thing, I'll call it equation 1 and I'll keep it here. And now the proof is going to be really easy. Now we are going to start with the proof. So I wanted to read the statement once more. the necessary and sufficient condition. Okay, so it will be better that you read this. We are going to prove the necessary part. So assume A has constant direction. And if A has constant direction, A cap will also have constant direction, because I told you a vector and the unit vector share a common direction. The magnitude might be different, but the direction will be same. So if the original vector has constant direction, then definitely the unit vector will have constant direction. But by the way, modulus of a unit vector is 1 and 1 is a constant. Oh, that means A cap has constant direction as well as constant magnitude. In the beginning itself I told you every vector will be associated with two quantities, the direction and the magnitude. So if A cap has constant direction as well as constant magnitude, then A cap is a constant vector and the derivative of a constant vector will be 0. And oh, where is that condition? It was here. Yeah, it's here. Now look at this. If the derivative of A cap is equal to 0, then this cross product will become 0. And if the cross product becomes 0, that's it. We proved it. So I'll repeat. A cap is constant, so the derivative of the constant is 0. And if this is 0, then by this relation, we proved it. So that's it. Now the sufficient part. In the sufficient part, what we do is we assume the right side and we prove the left. So let A cross dA by dt equal to 0. Now if this is equal to 0, then by this relation this will be 0. That means the right side is equal to 0. Now the modulus cannot be 0. I told you when A into B equal to 0, either A should be 0 or B should be 0. But our modulus cannot be 0, because if modulus is 0, then the vector will be 0 vector. And if the vector is a 0 vector, then this theorem will be trivial. Okay, so we get, okay, that is equation number 2. I will keep it here. Okay, now the modulus of a unit vector is 1. That is, the modulus of A cap is constant. So I think it's time to apply the first theorem. The first theorem states that if any vector function has constant magnitude, then the dot product with its derivative will be 0. So by theorem 1, we have A dot dA cap by dt equal to 0. So we have two equations, and the first equation tells the vectors are parallel. The second equation tells the vectors are perpendicular. They seem to contradict. Just imagine, can you hold two vectors parallel and perpendicular at the same time? It is impossible unless and until one of them becomes 0. But A cannot be 0. So the derivative must be equal to 0. And if the derivative is 0, then this will be a constant vector. And a constant vector means both magnitude and direction are constants. But we are talking about direction here, so definitely A cap has constant direction. Now I hope you remember A cap and A share the same direction, and that implies our vector has constant direction. So that's it. So if you find this video useful, please like, share and subscribe. And in the next video we will continue with multiple integrals, and we have that finding limits, areas, change of order and all these things. But I'm not going to include triple integrals now, because the total value of multiple integrals is just 10 marks. And normally a 5-mark question will come from this part, and then we will move on to 3-dimensional geometry or power series method, etc. Anyway, I'll be back soon with multiple integrals. So till then, bye.